All right, so today we're going to be going over ODE45. And ODE45 is it's a function in MATLAB that performs numerical integrations for you. And so that is so similar to something like Euler's method that you've probably learned about previously. And what it does is it allows for you to just give something just the differential equations, and then it'll solve it numerically rather than you having to do like the method of assumed solutions or Laplace or whatever to try and find an analytical solution to your equations of motion. That's helpful for a lot of reasons. Specifically, a lot of times equations of motion can't be solved analytically if they're more complicated. And it's also a nice, quick, and easy way to see how things are looking, and then you can solve things analytically later if you need to. So we're going to start with our typical equation of motion. So if we have something like x double dot plus 2 zeta omega n x dot plus omega n squared x, and so we're going to say that equals 0. So that's our...
There's like a block of, I don't know, it's like a black box that's covering the other end of the...
Sorry.
Okay.
Thank you.
No problem.
Okay, is that better?
Yes.
Okay. Got that fixed. Perfect. Thank you for pointing that out. Yeah, go ahead and interrupt me at any point with any questions or technical difficulties that we're having. So this is our equation set for a second order system, general equation. We've seen this a lot. And so we're gonna be plugging this into ODE45. And so what you do in an equation of motion is you solve for we're gonna solve for our highest order derivative. So in this case, x double dot is equal to minus omega n squared x minus 2 zeta omega n x dot. So that's our equation of motion. It is a second order equation of motion. And so what we're going to have to do, ODE45 only takes first order systems. And so you probably learned in like your differential equations class or other classes that you can break up a higher order differential equation into a system of first order differential equations. So that's what we're going to do, and we're going to do that by a substitution. And so I'm going to make a substitution that y, and I'm going to call it a vector of y1 and y2. And I'm going to say that equals, for our substitution, I'm going to say y1 is equal to x, and y2 is equal to x dot. And this is just the substitution that we're going to make to get a system of first order equations.
Can you explain that one more time? I'm a little confused by the matrices.
Yeah, so this is just a vector. Excuse me. So we need a system of, so because we have a second order differential equation, we're going to break it up into a system of 2 first order equations. And so because we have an x dot and an x, we just need to substitute those into 2 variables that aren't written as derivatives of each other. And so I'm just going to say x is equal to y1 and x dot is equal to y2. Did I not just? Weird. And so So the fact that it's a vector or a matrix doesn't necessarily matter. I'm just writing it this way because so that we can have y, which is going to be called our state vector. It's not entirely necessary, but it's just a vector with two variables in it that's substituted in for our x and x dot. Is that a little clearer?
Yes, thank you.
Okay, perfect. So now what I'm going to do, so because I'm going to take the derivative of this y vector, so y dot is equal to y1 dot and y2 dot. And that's equal, so y1 dot is equal to x dot, and y2 dot is equal to x double dot. And that's equal to, so x dot, we're just going to say is equal to itself. And that's okay because it's one of our substitution variables here. And x double dot is equal to negative omega n squared x minus 2 zeta omega n x dot. And so then now I've got these two equations, and they're both first order equations. I'm going to substitute back in our y1 and our y2. So y dot is equal to, and x dot we said is equal to y2. And then on this next row, we've got negative omega n squared x is equal to y1 minus 2 zeta omega n, and x dot is equal to y2. And so this is just, it's a system of first order equations. And this is something that we can plug into ODE45. Any questions about that and developing those equations there?
Which ones would we plug into ODE45? All of them or just that last one?
That's a good question. So I'm going to show you here in a bit. We're going to plug in both of them, both of these two equations, the y dot equals y2, the y2, and the second negative omega n squared y1, yada yada. That's also going to go in there. So it's going to be both equations.
I have a question.
Yeah.
Are you gonna do an example with like a inhomogeneous equation?
Yes, we can do an example there. I was planning to do that towards the end, but essentially, if this term up here is not equal to 0, then what you have is you would have plus some f term here, and then you would just have plus f there on that second equation.
Okay.
If you're inhomogeneous. And we'll talk about applying that to ODE45 once we have this all coded up as well. Perfect. Thank you. Any other questions so far? Okay. So just for a little bit of intuition for what ODE45 does, typically when you solve an equation of motion, you need some initial conditions. Same as the case for numerically solving. So we're going to say that y of 0 is equal to 1, 0. So that means our initial position is 1. Our initial velocity is 0. So if we were to graph that, it would look like, so if our point 1 is right here, you would have something there with a slope of 0. If this is y of t and t. And so if we're using Euler's method, you would have, so you know that x of t plus delta t, this is just the general Euler's method, is x sub t plus x dot of, or x dot times delta t, x dot of t times delta t. And so if we apply that to our equation here, we have y of t plus delta t, or y, I'll call it y next, and y2 next is equal to y current, y1 current, and y2 current, plus y dot, the derivative, y1 dot delta t, plus y2 dot delta t. And so what we do, so if we're starting at our initial condition 1, 0, it would equal, so y1 current is 1 plus, and y dot 1 is equal to y2, which right now is 0 times delta t. y2 current is 0 plus, and y2 dot would be negative omega n squared times y1, which is 1, and then minus zeta omega n y2 is 0, because y2 is equal to 0 right now, delta t. And so our next y, if our delta t is right here, so it's 1 plus 0, so our position is still 1, but our velocity, 0 minus omega n squared times 1, is going to be something like this. And so as you keep going, if you go to the next delta t, you would, what it would do is it would extrapolate this slope to find a point, and then you would get a slope there as well. And you can start connecting the dots. And so that's what numerical integration is you use your current value and your slope, or your derivative at your current value, to guess a value into the future. And so that's what ODE45 does for us. It uses what's called higher order approximations. Has anyone ever heard of a third, fourth order Runge-Kutta method? No, that's okay. It's like Euler's method, but instead of approximating straight lines like this, it does parabolas or cubics or whatever in between your points. Okay, so that's ODE45. We're going to be implementing this numerical integration using these first order equations and some initial conditions. So let me switch over here. I'm going to go ahead and stop sharing. Share my regular screen. Okay, so everyone, so you can go ahead and follow along. Sorry, I should have told you to pull up MATLAB, but I'll go ahead and go slow. So if you want to follow along, go ahead and get MATLAB pulled up. So we're going to start a script. I'm going to call it ODE example.m. I'm going to go ahead and save it. It's ODE example. I'm going to clear the command window, clear my variables, close all the plots. And so what I'm going to do, so I'm going to say help ODE45. It's going to take a second to load. Okay, so ODE45 solve non-stiff differential equations medium order method. So our function prototype here is t out, y out is equal to ODE45 ODE fun, so it's a function, t span, and y0, which is your initial condition. So with t span is a vector that has your initial time and your final time that you want to integrate over. There's your first order differential equation, and initial conditions y0. So we said we're going to say our t-span is equal to 0, 10. You only need to give it a first value and a last value that you're interested in integrating over. And what ODE45 does is it picks a good delta t for the problem based on how fast the system is changing. So just the first and the last value, 0, 10. Why not? We said was 1, 0. So that's an initial position of 1 and an initial velocity of 0. And ODE fun is a function that we're going to have to define. So I'm going to come to the bottom of the script here. And function. So dy, so what we had before was y dot equals, and I'll call this EOM, equations of motion, and t comma y. So anything that you're throwing into ODE45 has to have these two inputs of t and y, or at least you have to trick it into thinking it has those two inputs, because it's going to throw in the t-span and initial conditions into this function. So a couple things that we need to do. So inside this function, we're going to define our omega n. I'll just say it's 1. We're going to define our zeta. We'll call it 0.5. Keep it underdamped because that makes for more interesting plots. And then we're going to define dy, which is our, in this case, 2 equations. And you can have as many equations as you need to define your system. So our first equation, dy1, was equal to our first variable, is equal to y2. So I'm going to go ahead and say that. There we go. So our first differential equation dy1 is equal to y dot. And so in our equation, in our substitution vector that we made, that was our second value, was y2. So y coming into this is a vector. Our first equation is just equal to the second element of that vector. Our second element in dy was equal to negative omega n squared times y1, so the first element of that initial condition vector, minus 2 times zeta times omega n times y2, our velocity there. Questions about this function?
So when you're putting in the y1, the dy1, are you referring to like certain spaces in the matrices? Or is that just the name of the area?
Yes. So that is, so y, yeah, so that's a certain space in the matrix. If we wanted to clarify things, we could say y is y1, y2, and we could say y1 equals the first element in y, and y2 is equal to the second element in y. And then we could substitute in the equations that we've made there. Does that answer your question, Sarah Lynn? Okay. Any other questions so far? Okay. So what ODE45 is going to do is it's going to take its initial conditions. It's going to call this function, which gives it the derivatives of our position and velocity. So it gives us our velocity and the acceleration. And then it's going to use those to estimate the next step. And then it's going to take that step, throw it back into this, and estimate the derivatives at that point and continue forward, similar to what we did with the Euler's method. ODE45 requires that the values of the derivatives come back in a column vector. So we're going to transpose this this dy vector that we've created. There are a couple ways to make sure it's a column vector. We can do that. I often just initialize it like that. If you don't initialize it, MATLAB by default will make this a row vector. So you have to transpose it. Okay. I'm going to scroll away from this and go back to our main script. Just in case anyone's following along, make sure you get that down. So I've got our time vector created, we've got our initial conditions, and we have our function generated. So we can do ODE45. So I'm just going to copy this right here and paste it up there. So ODE fun, I'm just going to say is at EOM. The at sign, it tells MATLAB that you're talking about a function. And then I call this in lowercase letters, and y initial was also in a lowercase y and a 0 semicolon. And so what this is going to do is it's going to take your equations of motion, which we have 2 of them. Go ahead. Do we have a question?
Yeah, is that a is that an extra 0 there in front of the equations of motion that you have up there in the where you're calling ODE45?
Oh, this right here?
Yeah, what symbol is that?
Sorry, that is the at symbol. Let me go ahead and make my font a little bigger.
Sorry, I'm doing split screen, so it's a little tiny.
No problem. That's probably. Is that going to be good? Whoa.
Yeah, that's
There we go.
Yeah, perfect. Thank you.
Yep, no problem. Okay, so our T out is going to be a vector. So ODE45, sorry, let me rewind a bit. What ODE45 is going to do is going to take these equations and it's going to integrate them over this section of time with these initial conditions. And what it's going to do is it's going to spit out a time vector, and it's going to spit out a y vector with a column that is going to be the integral of each of your equations. So here, our first equation is the velocity. And so the first column of y out is going to be the integral of velocity, which is position. The second equation is acceleration. And so it's going to y out, the second column of y out is going to have the integral of acceleration, which is velocity. So what I'm going to do is I'm going to go ahead and plot t out and then y out, and I'm going to plot the position. So all the rows of the first column. And so if we go ahead and run this, we get this slightly underdamped system here. Our initial conditions of 1 with the 0 slope, and it drops below 0 and eventually settles out. There are a couple, so probably one of the biggest things is you want to make sure this is a column vector. If you don't do that, you try to run, you'll get an error, and it'll tell you the equations of motion must return a column vector. Okay, my bad. Want to be careful with your order here. So let me go ahead and say in a comment, we have our position and our velocity. And you want to make sure you keep that order consistent when you're dealing with those numbers in your equations of motion down here. Let's comment this. Any questions about this so far?
So the plot that you made, was that position?
That was position. Yep, and that's because I took the first column here. So I'll go ahead and put a title on that. Yeah. Any other questions? We can go ahead, so you could also plot in a new figure, you can plot the velocity, which is all rows and the second column of y out. So you can see that makes sense. So our velocity, we've got negative, 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 0, positive, and then slightly negative again. And you can see that here in the velocity. So this is in fact the derivative of this one over here. I believe it was Kathleen earlier talked about adding a non-homogeneous term. So like I said, that's just, you can add that here. And you can make this, anything you want, including a function of time, because time is a known value in this equation. So if I said f was equal to, let's say 4 times sine, let's say of omega, let's say that's equal to 5 times t, or 4 times t. So now we have a non-homogeneous term here of 4 sine 4t. And if we run everything, then we can see that we're getting some oscillatory response there. Any other questions?
So how would we alter, so we wouldn't need to alter our, I guess that is us altering it. I was like adding an F, do we need to alter any of the other ones that's in the main script?
Any here?
Yes.
No. So in the main script, we're just defining our the time that we're integrating over. So start at 0 seconds, end at 10 seconds. And we're defining our initial conditions. If there's a function, there's an input function or a non-homogeneous term that's defined in your equations of motion. Down here, there are ways of defining parameters of that outside this function so that you can use it with different, like maybe different forcing functions or something. And maybe we can talk about that in my office hours or something if that's something that's interesting to you.
Thank you.
Any other questions? Okay. So I guess just one more time going through everything. So it's just this one line to call ODE45. The first argument is a function that returns your equation, the values of your equations of motion in a column vector. Second one is a vector of your time span, which is the beginning and end time, and then your initial conditions. Are people, I don't know, are people following along? Are you getting this to work? Are you getting some weird errors?
Mine just worked whenever I did the F part, it worked. I did not try it before I put in the F, but it worked.
Okay,
Mine's worked.
perfect. All right then. I'm gonna go ahead and stop the recording.